We're now going to look at an application that is often seen when we study vectors. Our example reads, an airplane is flying at a speed of 200 miles per hour at a bearing of north 33 degrees east when it encounters wind with a velocity of 35 miles per hour at a bearing of north 47 degrees west. What is the resultant true velocity of the airplane? We want to begin this problem by constructing a vector for both the airplane and also for the wind. So let's begin with the airplane. We know that the airplane is flying at a speed of 200 miles per hour at a bearing of north 33 degrees east. Okay, so to begin, let's talk about this direction. We know that north is straight up, and we are going to see that airplane 33 degrees east of that north direction. So this is east. So if I'm looking at my north direction here, I want to rotate 33 degrees towards the east. And so that airplane is going to be flying along a path like that, with an angle of 33 degrees in between. All right, and so what I also know that is probably going to be important is that this angle is going to be 57 degrees, because we know that the two angles have to add together to make 90 to go from straight across here up to here. We've got a 90-degree angle in between. So we probably need to know both of those values. Okay, so let's write a vector for the airplane. Now, remember from the last section, we learned that we could write a vector in this format, where we have the magnitude, and then we do cosine of the angle, sine of the angle. So, and remember we talked about the fact that the magnitude is the same thing as the speed. So the airplane's flying at 200 miles per hour. 200 is going to be my magnitude. Now, what angle are we going to use? We're going to use the angle that comes in from the standard position, from that initial side sitting on the positive x-axis. So from this side to get to our vector, we've got an angle of 57 degrees. All right, so I'm going to plug in 57 for both of the theta values. And then I'm going to go to my calculator with this. All right, and so I'm going to multiply 200 times cosine of 57, and that's going to give me 108.9 for my first value. And then I'm going to multiply 200 times sine 57, so that's going to give me 167.7. Okay, so this is the vector representation for the plane. Okay, so we're going to come back to that in just a minute and use that. Let's go ahead and do the same thing for the wind. All right, so we know that the wind has a velocity of 35 miles per hour and the bearing is north 47 degrees west. So I am going to erase this just for a second, kind of get it out of the way. All right, so here's the west direction. Here's the north. We are 47 degrees west. So the wind is somewhere over here with an angle of 47 degrees. Okay. Now, when we set this up in our vector representation, in other words, when we do this sort of thing that we did for the plane, we're going to do it for the wind. Our magnitude on the wind is going to be 35 miles an hour. Now, let's think about this angle. We still want the angle to be sitting from standard position. So from here, we want to rotate all the way to that vector. So essentially, we have a 90-degree angle, and then we have an additional 47. So 90 and 47 make 137, and that's going to be the angle that I'm going to use in my vector representation. All right, so now I'm going to, in my calculator, 35 times cosine of 137, and that's going to give me negative 25.6. And then I'm going to do 35 times sine 137, and that's going to give me 23.9. All right, and so this is the vector representation for the wind. All right, so now we're ready to talk about where the airplane actually is. All right, so we know that the plane is flying and the wind acts on the plane. So the wind and the plane come together. To show that they come together, we're going to take their two vectors and add them together. So essentially, I am going to add the wind to the plane, and I will have my resultant vector for the airplane. Okay, so let's do that first. So I am going to add the two horizontal displacements first. So 108.9, and we're going to add a negative 25.6. That gives me 83.3. And then I'm going to do the same thing for the vertical displacement. So 167.7 and 23.9 added together gives me 191.6. So this is the vector that represents sort of the actual path of the plane. We know where the plane is flying, and then the wind acts on it, and this is what we end up with. And so this is the vector that we're going to use. Okay, so the question is asking us for the velocity of the airplane. So remember, velocity or speed are both other ways to talk about finding the magnitude. So we're going to take our vector that we found, which is here, and we are going to find the magnitude for that vector. So that's the first thing that I'm going to do. I'm going to plug it into my formula for magnitude, which says I'm going to take the 83.3 and square it, and add to that the 191.6 squared. And when I calculate that, I am going to get 208.9 miles per hour. And so that is our true velocity for the airplane. Now, another thing that's asked often with a problem like this, that they don't actually ask in this particular problem, but that you might see in your homework, is to find the actual location of that plane in terms of a direction. So in other words, to tell exactly where the plane is in relation to either a north or south, east or west direction. And so I want to go ahead and show you how to do that, just so that if you see it in another problem, you'll know how to proceed with it. And so we're going to do that by using our tangent formula. And so basically we're going to do tangent of our angle that we're looking for. And you know, our normal formula is y over x, or you could say b over a, depending on how you want to label the components of this vector. The 191.6 goes on the top, and the 83.3 goes on the bottom. And then you're going to go to your calculator and you're going to enter it in as an inverse tangent. And so we will be putting this thing in inverse tangent of this fraction. And when we do that, we're going to come up with 66.5 degrees. And remember that that angle measurement is going to come off of an angle that is in standard position. So you're talking about starting here and going up 66.5 degrees. So roughly like maybe right about here. And so think about how you could label that. And perhaps the easiest way to label it is to start with your east direction and say that we're going to be looking at the plane being east 66.5 degrees, and we're on the north side of that. And so just keep that in mind, that sometimes is a second part to this type of problem.